All right, so what are we going to do with this information about precipitating? In other words, how can we tell if we have let's say we know that something like silver and chlorine produce a precipitate. The question is, if we just dump a bunch of silver and a bunch of chlorine into solution, and we know that when this actually is in solution, that it's not really a solid. It actually does dissociate a small amount. And it is these amounts in solution that give us our KSP. It's the concentration of each of these ions in solution. So how do we know if we have enough? Let's take an example of a problem we might expect to see. This one says a solution contains 2 times 10 to the negative third molar cerium and 1 times 10 to the negative 2 molar iodate ions. Will cerium iodate precipitate? It gives us the KSP. So if we were going to write the equilibrium expression for this, there's 3 iodates. So KSP, well, let's write the dissociation equation first. So cerium iodate is going to dissociate into cerium and 3 iodates. And since this is a solid, it even says it right up here. Oops. You even see that little S, so it tells us it's a solid. Will this precipitate? So KSP is equal to the concentration of cerium times the concentration of the iodate ion raised to the 3rd power, because there is a coefficient here. And it tells us right here that the KSP is 3.2 times 10 to the negative 10th. In other words, when this is in equilibrium, the concentration of cerium and iodate in solution give us this ratio of product to reactant. Well, we have this much cerium and we have this much iodate. Will we get a precipitation? We're going to set this up like we did way back in chapter 13 with Q. We're going to call this reaction quotient. And for there to be a precipitate, Q has got to be greater than or equal to K. The concentration of these guys in solution has to be large enough to at least make it to this ratio, and bigger if possible. If not, then if Q is less than K, that means no precipitate forms. So let's try it. We've got a concentration of 2 times 10 to the negative 3rd molar cerium and 1 times 10 to the negative 2 molar iodate. Will we get precipitate? Let's solve for Q. So Q is going to be equal to the concentration of cerium initially times the concentration of iodate initially. And we said our cerium was 2 times 10 to the minus 3rd molar. And our concentration of iodine is 1 times 10 to the negative 2 molar. Remember, that's being raised to the 3rd power. So let's bust out our fancy McSchmancy calculator. Let's put this over here so I can see what I'm doing. And let's turn it on. So we're going to say 2 times 10 to the negative 3rd. And we're going to multiply, times 10 to the negative 3rd, we're going to multiply this by 1 times 10 to the negative 2. And we're also going to, let's get back to, make sure that's times 10 to the negative 2nd. All right, and we're going to cube this whole thing. So let's take 3. All right, let's see what we get. Oh, aren't these calculators just fantastic? We get 2 times 10 to the negative 9th. In other words, we get 2 times 10 to the negative 9th. If Let me get rid of this guy. Our KSP is 3.2 times 10 to the negative 10th. Are we larger than that? In this case, Q, 2 times 10 to the negative 3rd, compared times 10 to the negative 9th, excuse me, compared to KSP, 3.2 times 10 to the negative 10th is clearly larger. So Q is greater than or equal to KSP. So that means a precipitate will form. All right. So that's really all we're doing. Okay. Let's see if there's anything else we want to look at. All right, let's try a monster like this. Obviously, this reaction involves barium chloride and potassium sulfate. And in a precipitation reaction, it's always the result of a double displacement reaction. So are we going to get precipitation from this at all? It's safe to assume that nothing involving potassium or chlorine is going to produce a precipitate, but the barium and the sulfate will. So what we want to find out is, are we going to get precipitation? Let's assume that we know the KSP for this particular solution. KSP would be equal to, obviously, barium and sulfate. Mercifully, they both have a charge of 2, so there's no coefficients. And we have a KSP of 1.5 times 10 to the negative 9th. Well, we want to find Q to find out if we're even going to get precipitation. So let's get this into our concentration. And so this one's got quite a lot going on. Obviously, we have 75 mils of this and 125 mils of that. That means our final concentration is, or final volume is 200 mils. So let's do a little millimolage. Millimoles is going to be equal to molarity times milliliters. And that means that we have, for barium, since it's going to dissociate completely, we've got 0.02 molar times 75 mils. Boy, I'm going to need a calculator for this one. And I'm not going to use my online one because it's not as fast. So 0.02 times 75 means we've got 1.5 millimoles of barium in what is now 200 milliliters. So this is 0.0075 molar. And for our, this of course is the barium. Let's do the same thing for the sulfate. We've got 0.04 molar and it's 125 mils, so we'll say 0.04 molar times 125 mils. This is 5 millimoles in what is now 200 milliliters. And this is 0.025 molar. So are we going to get precipitation? Well, we're going to plug it right into this equation up here. Let's plug this into here, and let's plug this into here to see if our Q is greater than our K, because if we're not going to get precipitation, then there's no point. So there's no coefficients, which is really nice. We'll say 0.025 times 0.0075, and we get 1.875 times 10 to the negative 4th. So if our Q is 1.875 times 10 to the negative 4th, then Q is clearly greater than K, and that means that we'll get a precipitation. So what's going to happen in this precipitation? Let's do a before and after table. We know that barium is going to combine with sulfate to make barium sulfate. Let's do a before and after. Because when we started this, we had 1.5 millimoles of barium, and we had 5 millimoles of sulfate. Obviously, when these combine to make the precipitate, there isn't going to be any barium left, so this is going to be 0. we'll have 3.5 millimoles of sulfate left, and this is going to make 3.5 millimoles of barium sulfate. So these are going to be our new initial concentrations. And so let's plug these into our final volume. This is 200 milliliters, and this is 200 milliliters, and this is going to be, these will both be the same, 3.5 divided by 3.5 divided by 200, this is 0.0175 molar sulfate and 0.0175 molar barium sulfate. Okay, so what does this mean? Well, when we plug this into our equation for KSP, obviously this is a very small number. Our KSP is on the order of times 10 to the negative 9, but we're going to treat this like this is a common ion effect. So here's how this is going to work. We're going to say KSP is equal to 1.5 times 10 to the negative 9th, which is equal to the concentration of barium in solution, times the concentration of sulfate in solution. Well, we have too much sulfate when we add these two together, so it's going to act like a common ion effect. So that means that if 1.5 times 10 to the negative 9th equals x times x, and we could solve for x just like we did in the first set of problems, we've already got some sulfate in solution. We've already got 0.0175 molar sulfate in solution, this guy right here. So we're going to just put this in here, 0.0175 molar. And of course, we would subtract that from x. But, I'm sorry, we'll add that, not subtract. But this is a small number. This isn't going to change very much. So that means the x is negligible. So if the x is negligible, we're just going to approximate. We're just going to say, okay, well, we already had some sulfate in solution. What's that going to do to our concentration of barium in solution? This is the concentration of sulfate in solution, and it's going to change things only a little bit. So 1.5 times 10 to the negative 9th equals x times 0.0175. Let's solve for x. And so we'll say 1.5 times 10 to the negative 9th divided by 0.0175. I get x, which is the concentration of barium at equilibrium, 8.6 times 10 to the negative 8 molar. And that's all you have to do. Looks like a lot. All right, take that for a spin.